6/9 now. Didn't make any mistakes here, did we? Hey folks, welcome out there this afternoon. We are so glad to have you tuned in to T and Learn Mathline. You notice I'm not alone. I have a cohort here today. But by the way, I'm Ernie Roberts, just in case y'all have forgotten. And I am your host for T and Learn Mathline. And this is Tara Carver Peters from Sullivan South High School up in Kingsport, Tennessee, Upper East Tennessee. We love it when you hear from us. She's here with us today, all right? And we are so glad. We're going to be doing tag teaming somewhat here, but we're glad you tuned in. And you know what? Let's see what we're going to do about today.
Sounds
Tara,
great.
let's see what we got going. It says it takes two. Well, there's two of us, and we're going to be talking about two diagonals working in a parallelogram today. That's the storyline and what happens with those diagonals. But you know what? Before we do that, we've got to go back and do a few short review moments. So, guys, let's see what we've got going on. First thing we've got here, all right? First of all, as we summarize what we've learned about parallelograms over the past summertime, right? It's summer school, right? Everybody's laid back. Everybody's having a great time. Now, let's look at our parallelogram down here. We've already got it written for you. And by the way, some of you, shame on you if you're just now tuning in, but hey, we're glad to have you, so I won't say shame on you too much there. But let's see, first of all, we make the nice notation. It sort of looks like that. And we make sure when we name a parallelogram, we name it in a clockwise or counterclockwise notation. So A, B, C, D is what I did. Notice that looks like counterclockwise. No, that's clockwise, right, Kara? Yeah. And now if I wanted to go, I could also go A, D, C, B, but as long as we don't jump around, all right? That's how we name those things. It says both pairs of opposite sides are parallel. Notation, got the little kicks here. And how about it right up here? By the way, opposite sides do not intersect in a quadrilateral. Consecutive sides are the ones who would intersect. So these little markings basically indicate they are parallel. That's the definition, right, Tara?
That is the definition of a parallelogram. It's a quadrilateral where both pairs of opposite sides are parallel to each other.
And you know, when we've got those going, let's do one more quick thing on it. We're going to put AB running parallel to CD, because those are the opposite sides, right? Give me another pair of opposite sides on this.
Well, I would say also that you could have line segment AD runs parallel to line segment BC.
She's good, all right? And as I said, we're going to find a little bit more about what Tara teaches up there in a little bit out in Sullivan South. She's quite an accomplished mathematician, folks. Hey, we got her on T and Learn Mathline. I'm feeling pretty good, all right? So let's draw a diagonal, by the way. AC will be our diagonal of choice. We could have done BD also. We get the same story here. But we do get basically two nice, pretty congruent triangles. And so for those of you who don't believe me, all right, let's put some angles on here. We're just a quick review here. 1 and 2, because why do I know 1 and 2? I need to put a 2 there first, though, right? So why are 1 and 2 there? What kind of angles are those with the parallel lines, Miss Tara?
Those are alternate interior angles, and what you have there are two parallel lines that are being cut by a transversal, and we know that
and that
means
diagonal is the transversal,
that
right?
diagonal is the
Yes.
transversal. That's exactly right.
And that's a pair of alternate, but you know what? There's another pair of alternate interiors lurking. How about it? 3 and 4, and they're based on these that are, well, they're not vertical, but they're sort of diagonal, right? Or run across like that. There we go. Yeah. So we've got those working, and we've got that little reflexive AC right down the middle, which gives us angle, side angle, angle, side angle. Remember, we've got to have one of those methods to be able to say the triangles are congruent. Now, one more quick shot here, because we're going to move along here, folks, pretty quick today. We aren't doing a proof of this. We did that on another show, so you can go back and look at our old editions online and find out about those. But let's name those. How about the ABC triangle first? And Tara, we got to watch out, right, for the switch. I call it the switcheroo, because parallel lines team to twist things up.
Yes, they do.
The 1 and 2 angle, because the alternate interior angles working there, force A and C to become a match when we name those congruent triangles. We're many times used to just saying ABC and ADC, but it doesn't work here.
Right.
Now, D and B are going to go together, and we're going to finish this one out with what letter then? What's left over? How about it?
It's going to be what corresponds to C to be A. Was that correct?
How about an A right there?
Yes.
And there's our basic situation.
So the important thing there is to show the correspondence.
Right. And you've got that, like I said, that angle, side angles were in there. You say, well, Ernie, why do you go to all that trouble? because now we can say something about opposite angles, those angles B and D up there in the corner.
Right.
They're congruent by CPCTC.
Congruent parts of congruent triangles are always congruent.
Exactly. And then we've got also our segments, AD, BC, also AB and DC. Opposite sides will be congruent. And by the way, I bet that's our next sheet, all right? So bring it back to us just a second, guys, and we'll bring that next sheet up there. Tara, tell a little bit about what your teaching forte is in the math up at Sullivan South.
Sure.
What's your favorite thing to do?
My favorite thing to teach is probably AP Calculus. I teach AP Calculus AB and BC. I also teach Honors Pre-Calculus, and I teach Algebra 2.
Wow, you've got a full load of a schedule.
I sure do.
And again, we appreciate Upper East Tennessee because we get so many calls from up there. So many of our students, young and also old alike. So don't know if we've had anybody from Sullivan South yet, but you know what? Probably they got a great teacher there that they can explain everything to you. So
Thank you, Ernie.
We're so glad to have you with us today. Now, back to our parallelograms here just a little bit. We've got the opposite sides that we're going to mark real quickly, and we're going to take this one through fast. How about it? EF and HG, those would be congruent opposite sides, but we also got another pair. What are the other pair here, Miss Tara?
We've got EH is going to be congruent to FG.
FG. My hand gets in the way a lot of times, they tell me. I'm there. So, but we've got those going, folks. Those are the opposite sides, okay? Now, opposite angles, we can pick up also, sort of looks like that, H and F, it looks like we're going to go with. And then also we've got little E and what's that little guy down there? Oh, G. Yeah, let's go with G. So there's a lot of good parts there. That's why we have to do those triangles, because all those corresponding parts, those congruent triangles that are congruent, that's where we get these relationships. Now, some books call these theorems, some call them corollaries, some just call them properties. It just depends on what textbook you got. But basically, that's the structure. Those are the rules for your parallelograms. Now, we got one other type of angles we're going to look at in just a second. Remember, there's consecutive. We've been looking at opposite. Now, we got consecutive angles like E and H. Also, angles, what about E and F? They're consecutive. E and H we've already done, right? H and G, and how about it? F and G. All of those great things. So we're going to pick up on that. So let me get a little shift going there. Yeah. And here we are. Let's take a look at those real quickly. And we've got it here. We're going to call these supplementary angles, by the way. They come in pairs. So let's take a look at these as quickly as we can. So tell me about it. Tara, I've got A, B, C, D again. So what about angle A? Angle A has a couple choices, right?
Right, it certainly does. So
supplementary to?
It's supplementary to angle B.
Okay.
And it would also be supplementary to angle D.
Yeah, and also, by the way, sometimes we'll see it with an M on there because the measures are supplementary. They add up to 180.
Right.
Usually when we do that, we just put plus there, and we usually just use the letters like this. But as she said, we could also do it with angle D. A and D could work together. Now, let's take a look at it. There's A. There's B. Obviously, if this were a rectangle, which, by the way, is a parallelogram, correct?
Right.
We're all good on that. That's when consecutive angles can be congruent because it'd be 90-degree angles. But obviously, one of these is acute and one is obtuse. So that's the easy way to tell that you're putting it together. By the way, we know that because these lines are parallel. Same side interior angles. If the lines are parallel, same side interior angles will be supplementary.
Very true.
Now, we've got a few more parallels as we wrote in earlier. And that's what's the beauty about parallelograms. All these rules don't hold unless you got parallelograms, folks. That's the key, all right? So these are going to allow us to pick up, well, how about it? B and C. So angle B could be supplementary to angle C. And I bet some of you are noticing, what about C and D? Well, what about C and D? We're going to allow those to be supplementary also. And I just ran out of ink, so how about it? We're going to change color just a little bit. Well, not too bad, not too bad. And that's our story. That's our story here. So did we get them all? Well, wait a minute. We got A and B. Oh, we could get A supplementary to D also. I got a little carried away. All right. That's why it takes two here. She's going to keep me honest today. We cover them all, Miss
I think we did. A
Tara?
and B, and we've got B and C, C and D, A and D.
Awesome,
Okay.
awesome. And those are supplementary pairs, which means they add up to
180
degrees.
Exactly
Exactly.
right.
So, folks, we're going to do some math here in a minute. You're going like, when are we going to do math? we're coming. It's coming, all right? So be patient. Let's take a look at another parallelogram picture here. We're going to play with a little bit here. It says, draw two diagonals. Remember I said it takes two. That's the title of our show today. And we're going to name 4 pairs of congruent triangles. Let's see, we're going to draw two diagonals. Tara, what we got going here? Which diagonal should I go with? Looks like AC going, right?
Let's go with AC, yes.
All right, let's do it. And also BD. Two diagonals, two hosts. How about that? And you're doing a great job. Thank you for being with us today.
Thank you for having me.
And we're going to let them intersect there at X. Now, you know what? I see 4 triangles.
You see 4 triangles?
I see 4 triangles. You see more?
I can see 4 more triangles.
Ah, all right. I'm looking at 4 of these little guys, right?
Right.
But there are some more, right?
There are some more.
Okay, let's go see. Oh, the big ones.
You've got one right there.
Coming around.
And right through there. You've
ABC.
got very good.
Keep going.
You've got BCD. And you've got ADC.
8 triangles, folks, in this picture. One of those trick questions already we're asking you. But now what do we got? We got 4 pairs of congruent triangles. So I'm going to go back. Just a few minutes ago, we put that slide together. Remember, we're going to go with big triangles, all right? So let's see. One pair of congruent triangles would be ABC. And we can say that is congruent to, how did we do that? We got to switch it around, didn't we? CDA, working along there, all right? Now, let's go for the other big diagonal, which is DB. So let's see, how about it? We'll start ADB. And that is going to match up, let's get the order right here.
Okay.
ADB should match up to what? CBD? That's the thing, when you're naming triangles and they're in a parallelogram setting, you gotta be careful, Now remember, all these lines are running parallel, so that gives us congruent parts, but it gives them an alternate interior angle slants, which twists these triangles up a little bit.
And it's very important to show how they correspond to each other.
Yeah, because that's where we came with here to here. These 2 angles work, but these 2 angles also work. And then, well, then we had that reflexive strip going down through the middle when we named those big ones. And we can do the same thing going this way. You see, both of these are transversal. She mentioned the word transversal earlier. That's one of those things, a long time ago, we did a lot of transversal work on this show. So, but anyway, we are good to go on that. Now let's go for the small ones. Let's go for the small ones, because there are also some things going on here. Notice I put little 2 dots here, and we got vertical angles running here. I'll put 3 dots in there just for the fun of it. You say, well, Ernie, what does that mean? I guess I got 2 angles. You know what? I need a pair of sides in order to make those triangles, these 2 small triangles here. I'm calling them my bow tie triangles. Got to make, they look like they're congruent. So let's go for it. Let's see, angle ADX. We're going to say it's congruent to ADX. How about it?
Let's see, if you've got ADX, how about CBX?
CBX looks good to me, because X and X is in the middle, vertical angles,
Very
right?
good.
So CDX. And let's play the upper and lower triangles, because they also work. AXB.
Should that be, let's see,
Did I do that right?
CBX.
CBX,
Yeah,
thank
CBX.
you.
Okay.
That's why you're here.
Okay.
It takes 2.
It takes 2.
Let's see, what do we got? AXB. And we're going to make that congruent to
CXD.
CXD, sounds good. So folks, there's 4 pairs of congruent triangles. They're kind of crazy because they're twisted in there. But that's going to lead us to what happens when the 2 diagonals come together. And you know what? Got one more parallelogram. We're going to make a conjecture. What's a conjecture, my dear?
A conjecture is kind of like we're just going to put forth our idea of what we believe to be true, and then we're going to have to test it and see if it is.
That's one of those things my students say, well, it looks like it should be.
Right.
You know, and if you draw a true parallelogram, these properties should really look like they work.
Exactly.
All right?
That's exactly
But the whole
right.
idea is we prove them, and we show that, hey, they work no matter what twist or turn we might have, as long as we have a parallelogram.
That's exactly right.
All right, so let's do real quickly about these diagonals. And this one's one of those, I say, is not quite as obvious, but once we tell you about it, guess what? You're going to know, oh yeah, that works. Makes sense. So let's first of all draw the 2 diagonals back in here in the blue figure one time. Got one time going here. We'll let it intersect at, oh, why not? Call it P this time, all right, since I got an X out there on the side.
Gotcha.
All right, now, actually the conjecture that we're hoping you're looking at there, you're saying, well, Ernie, do those triangles look congruent to you? Absolutely not. Well, the triangles might. Some of them do, but not all of them, are they? But what about the diagonals? Do the diagonals look congruent?
That's an interesting, you know, sometimes they may be, but sometimes they may not.
Right. And in this case, the way we've got it, I believe AY looks a little bit longer than
I would have to agree with you.
XZ. It's a little bit longer. So we can't say that they're congruent diagonals, but there is something going on. And P is a rather important moment here, because P is basically playing out to be a midpoint of XZ as well as AY. You say, Ernie, why is that the case? Tara, why is that the case? Because of the congruent triangles we found. Remember, these top triangles are congruent, so hey, these match, CPCTC, corresponding parts, congruent triangles, congruent. Same thing with our little bow tie over here. These guys here on the left and the right, they match up, corresponding parts. So they are equal to each other. So that's where we come to our full circle. That's where we come to our full circle here. And let's see what our final conjecture was supposed to be. That they bisect each other. Bisect each other. So let's do a little arithmetic. You've been waiting for Mathline, right? From numbers to pop up. Let's do it here.
Let's do it.
All right. Tara, we've got AX is 12. Make sure I put these in the right places. Got it there? Which is good. And then I've got BX is 8. Obviously, those are different lengths. Ta-da. So they aren't on the same diagonal, are they? Because diagonals are bisecting each other.
That's exactly right.
However, all we want to do is go from 12 and 8 to figure out what's the length of. Well, we're going to figure out what is AC equal to and what would BD or DB, however we want to write it, equal to. Now, some of you, I want you to notice a little bit. This is maybe one of my old school type things, but it's still very true. Some of you are going, well, Ernie, why don't you put a bar over AX and BX, all right? Because that means it's a segment. We are looking for a length. And when we leave that bar off or that segment bar off, we're talking about a number, all right? So how long is AC? Folks, I can see where AC is as a diagonal and a segment. It's in the picture, all right? So what we want to do is figure out what is the length, as it was saying there. So I've got A to C, looks like, well, there's 12. What's going to be from X to C?
It's got to also be 12.
Because we're bisecting, right?
Correct.
All right, and let's go with the DX. How about it? I like 8.
I like 8 as well.
So here we go, and it is pretty obvious. Those aren't the same lengths of diagonals, are they?
No.
We got 24 for AC, and looks like what on the other end? 16.
And it's interesting to note that whenever they do become equal to each other, your parallelogram has morphed into a rectangle.
It will be doing that,
That's exactly right.
Because the only way that's going to work is if we have right angles popping up. And by the way, some people may not realize it, but I want to make sure everybody does. All parallelograms are not rectangles, but all rectangles are parallelograms. Yes, they're part of that parallelogram family. In fact, we're going to do a whole big show on rectangles on down the road, okay? Not today, but it'll be coming your way, Tara, a little bit of, what is some of your favorite things that you get to teach? I know you love calculus, and I know you love the trig.
Right.
What are some of the things that are maybe your favorite part of those courses? And you don't have to get too technical, because I'm going like, a lot of those folks out there going like, calculus?
Calculus.
Is that what you do, a calculator? No, folks, no. Well, we have calculus. It comes after pre-calculus, which comes after you do your Algebra 1, Geometry, and Algebra 2. So tell me a little bit about what you enjoy about those.
Probably my favorite is anything to do with the geometry of it. I enjoy volumes of solids of revolution a great deal. I enjoy series and sequences. I love integration. I probably love the second part of calculus even more than the first. Even though derivatives are a lot of fun, I find that the antiderivatives are even more fun.
Ooh, being anti, that sounds really good too.
Exactly.
Yeah,
a little rebellious there
which
against
is what
the
you call
derivatives.
Integration.
That's
also,
exactly right.
Yeah.
You've got it.
I'll tell you, I remember some of those things a long time ago, folks. I did a lot of calculus.
Far, far away,
but
right?
there was good calculus and all sorts of good things. But you know what? It's a fusion of algebra and geometry.
It really is.
And so all of those things you're learning in high school, all of those important little things, come together,
Right.
fuse together, I like to use that word,
Yeah.
and make the calculus happen.
Well, it's really important to understand that probably the concept of slope in Algebra 1 is probably the underlying principle behind most
Rate
everything we do, rate of change. Exactly, and it's very important to understand that to do well in calculus.
Super, super. Well, you know what? We're doing geometry today, right? A little bit. Let's look at a few more, and we're going to fuse a little algebra and geometry together. Not making calculus per se, but let's look at our parallelograms here, and let's do a little algebra,
Sure
all right?
thing.
We love to keep that algebra on the forefront. Let's see. Storyline. We've got a parallelogram. There's our symbol. Everybody see that? Yay. D, E, F, G. Yep, we put them in the right order. Sometimes Ernie forgets things like that, but you know what? I've got someone helping me today, all right? So we've got it good. Now, we've got dx. dx, which we're going to say there is our 3y plus 2. But now, where's df? df is the whole diagonal, isn't it? 3y plus 2 is 1/2 of that diagonal. So we could jump right in and say, oh yeah, 3y plus 2 equals 14, but that's not correct.
That's not
Is
correct.
it? That's not correct. Actually, what is the length of fx if df is 14, folks? What do you think out there at home? Good question. What do we think?
Well, we would think that the length of xf would have to be half of the length of df.
Okay.
So if df is 14, that would tell us that fx or xf has to be 7.
All right, so I'm putting a 7 right there. Now, you see what we could do? We could say 3y plus 2 plus 7 equals 14, but that's kind of redundant because we have a little property here, a little theorem, however you want to call it, that says they are actually equal because the diagonal bisects itself, all right?
Correct.
So let's see, or if they bisect each other here. Let's do it. Would it be 3y plus 2 equaling to 7?
I think that would be correct.
And you know what I did? I think I made it. We're going to have a fraction. Folks, we do fractions on Mathline, don't we? We're not
Fractions are
immune
our
from it.
friends.
They are, exactly. Action
are.
of fractions. I love it.
Exactly.
I love it. So let's subtract that 2. Let's subtract that 2 over here. And we're going to have 3y. Oh, that one's easy. 5, right? And we divide by 3. Let's see what happens. Dividing both sides by 3 there. And sometimes, you know, sometimes you do that. You put the division moment there, and sometimes you don't. But I'll tell you what, when it doesn't come out even, it's nice to see what that fraction actually is. Because sometimes that number might be smaller, and then I have students say, what do we do? Well, you got a fraction, all right? So we got y equals, looks like 5 over 3, or 5 divided by 3, or 5/3, we like to say here, which is 1 2/3. Quick check, all right? 3 times 1 2/3. Oh my goodness, that's a fraction. I'm asking y'all to multiply fractions, right? Let's make it improper. And then we will add 2 and hopefully get to 7. I believe we will because these 3's take a nice cancellation leap. 5 plus 2. Everybody knows 5 plus 2 is 7. You got it, you got it. All right,
Excellent.
Tara, very good job there, good job. Now, we got one more we're going to look at, hopefully real quickly here, about these lovely diagonals. It takes 2, and again, Tara Carver Peters, I've got it down. You are coming to a point, you've been teaching how long?
30 years.
Wow, and you still love it.
I still love it. I certainly do.
That's what we need, folks. That's what we love to hear, is that we have teachers who still love what they're doing. And there are so many of you out there, and I appreciate you. I really do appreciate you. I feel fortunate I get to do something like Mathline here. But we also want you to remind your students this fall, we're a resource. We try to help. We do a call-in. We do tutorials, that type thing. And sometimes we make a little, I do. I get a little carried away. I get excited. I make a little error here, a little there. But I do find out that so many people do appreciate what's going on here. Include that with your students. Include that with your students and all. We also have Facebook. Let's take a look at our Facebook charts here. And I said we're going to do one more problem. Maybe we can do that too. We do have Facebook that you can communicate us with. And also, hey, there it is, www.facebook.com with a /TNLearn/. And don't forget our email address right there, mathline@tnlearn.org. We'd love to hear from you. We love to work problems for you. We love to help you out. That's what we're here for. Nothing less, nothing more. All right. And we'll be back live come August. Let's look at this last problem real quick here and see if we can at least set it up, and then we're going to get back to back to Tara here. It's an EG moment. The full thing, is 2p plus 5. And XE is half of that, isn't it?
Right.
So we're going to say 1/2 of this equals 15. All right, double it real quick. 2p plus 5 equals what, 30? Subtract that 5. Woo! It's going to be 2p equals 25. This is where, Tara, you're really good for me. And what do we get? 12.5, right?
You're going to get 12.5.
Excellent. There we go. That's the diagonals. It took 2 of them to make things happen. It takes 2. Thank you, Tara, for being with us here.
Thank you for having me.
And a great job that you do up at Sullivan South High School. And y'all are fortunate to have her. And you know what? We're glad to have you with us today. And we'll see you next time.